Okay, this is still our notes from section 4.6. We're going to finish up this worksheet now. We're on problem 4. We want to graph the function f of x that's given. Step 1, the domain of f is all real numbers except for 2 and negative 2. I'm throwing away those two numbers since I can't divide by 0. Because I'm throwing away 2 and negative 2, I'm going to have vertical asymptotes at x equal 2 and x equal negative 2. Step 3 is to get the equation of the horizontal asymptote. When we compare the degree of the top to the degree of the bottom, we have a degree 1 polynomial divided by a degree 2 polynomial. Whenever the degree of the top is less than the degree of the bottom, y equals 0 is a horizontal asymptote. There's not really any work to do. You just write y equals 0 in that particular case. So now we're on to step 4. We want to determine if the function crosses the asymptote. To figure that out, we set the function and the asymptote equal to each other and solve this equation. Multiply both sides by the denominator and then add 1 and you get x equal 1. So, okay, this graph will cross the horizontal asymptote. That'll happen once. And when x is 1, y is 0. So even though I'm going to have a horizontal asymptote on the graph, I still want to make sure that the point 1, 0 is a point that's on the graph there. Step 5 is getting the intercepts. When I set the function equal to 0 and solve, I've already done that. From here, I get x equal 1 as the x-intercept. So this point is actually also an x-intercept on this graph. And then to get the y-intercepts, let x be 0. When you plug in 0 into the function, you get 1/4. And so these 2 points are my 2 intercepts. I only know 2 points on the graph. That's not a whole lot, although I do know some more information about this graph, like the asymptotes and that. And I mentioned that it's typical to need to gather up a few more points along the way. If I were to let x be negative 1 and plug that into the function, I'll get negative 2/3 in return. So here's that point, negative 1 2/3. What I think is happening in this middle section here, because I've got these asymptotes already drawn, is that the curve is going to be coming down the left vertical asymptote. It'll be on the right side of it and pulling away from that slightly. It's going to go through these points and then approach the right vertical asymptote, but on the left side of it. Okay, now make sure that all the sections are complete when you're graphing these functions. I've got a left section, a middle section, and a right section. So let's get the left section finished now. If I were to let x be negative 3 and plug that into the function, I'll get negative 4/5 in return. So here's that point. Now that single point will tell me that, as long as I'm on the left side of this left vertical asymptote, I'm also going to be below the horizontal asymptote. The curve has to flow with the asymptote, so keep that in mind. You shouldn't need a ton of points here. Of course, if you're ever unsure about any of this, the more points that you plot, the better. But what I think is happening here is that the curve is going to be coming along below the horizontal asymptote, pulling away from that slightly. It's going to go through that point that I just plotted, and then approach the vertical asymptote from the left side of it. Okay, and then to get the right side set, I'm going to let x be 3. When I plug 3 into the function, I get 2/5 in return. I plotted that point. That point tells me that the rest of the graph is going to be in the upper right-hand region here. Again, the graph has to flow with these boundaries that I've already got in place. So the curve is going to be coming down the vertical asymptote on the right side of it, pulling away from that slightly and approaching the horizontal asymptote. Okay. Here's another problem. Problem 5, we want to graph the function that's given there. When you set the denominator equal to 0 and solve, you get x equal negative 3 and x equal 2. That's what we don't want, since we know we can't divide by 0. And because we're throwing away those two numbers, we're going to have two vertical asymptotes at x equal negative 3 and x equal 2. Step 3 is to find the equation of the horizontal asymptote. The degree of the top is the same as the degree of the bottom for this one, with those both being degree 2. And so I'll need to divide here. I've already got my division calculation set up, and I've gone through that division process. When I disregard the left over here, I have y equal 1. is the equation of the horizontal asymptote. Okay, and remember we use a dotted line to represent an asymptote there. Okay, step 4 is to determine if the curve crosses the horizontal asymptote. When I set the function and the asymptote equal to each other and then solve for x, I get x equal 5. So this is going to be another case where the graph will cross the asymptote. When x is 5, y is 1. So 5, 1, I want to make sure that that point is still on the graph, even though I've got a dotted line there. Step 5 is getting the intercepts. When you set the function equal to 0 and solve, x squared minus 1 equals 0 means that x squared would be equal to 1. So when you take the square root of both sides, x would be plus or minus 1. And when you plug 0 into the function to get the y-intercepts, you get 1/6 in return. These 3 points would be my 3 intercepts on the graph. And those 3 points that I just found kind of tell me the story of what this middle section would look like. I've got these boundaries here to work with, so the curve looks like it's going to be coming up the left vertical asymptote on the right side of it. It'll pull away from that slightly, reach a peak, and then fall back to approach the other vertical asymptote from the left. To get the rest of the graph figured out here, plot some more points. And so like if I let x be -4, plug that in, I get 5/2. Here's that point. Again, the graph has to flow with these 2 boundaries. So it looks like the curve is going to be above the horizontal asymptote, rising. It's going to pass through that point that I just plotted and then approach the vertical asymptote from the left. I've got a left section, middle section, right section. These 2 sections have already been complete. So the right section, I've got this point plotted for my work in step 4. And if I were to let x be 4 and x be 6, I see I get 1 point above the asymptote, 1 point just a little bit below the asymptote. So it looks like the curve is going to be coming down the right vertical asymptote. Is going to pass through these 3 points that I've got there. And then once you're below that horizontal asymptote, of course the graph still has to flow with the asymptote, so it's going to be approaching that asymptote from below it, but it'll never cross it again. Okay, problem 6 is another one here. This is an example of one that has an oblique asymptote. The domain of f of x is all real numbers except for 1, since we can't divide by 0. And x equal 1 would be the equation of the vertical asymptote then, since we're throwing away that number. Now here I've got a degree 2 polynomial divided by a degree 1 polynomial. Whenever the degree of the top is 1 more than the degree of the bottom, as is the case here, you're going to have an oblique asymptote. An oblique asymptote is a slanted asymptote. We'll be able to get the equation of that through division. I've already set up my division process here and gone through that. When I disregard the leftover here and write as an equation y equal x plus 1, that would be the equation of this boundary here that I've already got drawn. And of course that needs to be a dotted line also. That's a boundary on the graph. To see if the function crosses the asymptote, set those equal to each other and solve. 2 does not equal -1. X was eliminated completely, so we're not going to have any points where the graph will cross the asymptote in this problem. And to get the intercepts, okay, set the function equal to 0 and solve. X squared plus 2 equals 0 means that x squared equals -2. Now, if you were to continue solving that, you'd have imaginary solutions. We're not doing anything with I or imaginary numbers when we sketch this graph. It's all about the real numbers here that we plot. So there's not going to be any x-intercepts. When you plug 0 into the function, you get -2 in return. So 0 and -2 would be the only point I guess I know on this graph at this moment. So then I'm selecting some more numbers to gather up some more points here. If x is -1, y is -3/2. So here's that point. The graph has to flow with these boundaries, right? So the curve is going to be coming along below the oblique asymptote. It'll pass through these points. and approach the vertical asymptote from the left. Of course, it's not going to get real close to where those two asymptotes intersect because I don't have any x-intercepts. So this here is not useless information to me. On the right side of the vertical asymptote, I plot some more points. If x is 2, I get 6 when I plug that into f. When x is 3, I get 11/3 when I plug that into f. So here's those 2 points. Again, the graph has to flow with these boundaries. So the curve looks like it's going to be coming down the vertical asymptote on the right. It'll create a valley here and then be approaching the oblique asymptote from above it. Okay. I got 2 more here. So problem 7 is another one. We want to graph the function f of x. The domain is all real numbers except for 2. I know I can't divide by 0. Although in this problem here, we're not going to have a vertical asymptote. The reason is because the function was not in lowest terms. When you simplify the numerator, x minus 2 will cancel with x minus 2 in the denominator, leaving us with y equals x plus 2. Okay, now y equal x plus 2 is a line, right? So what we're drawing here is going to be something that is kind of like a line, although it's not completely a line because we're still graphing the function f of x. Now f of x equal x squared minus 4 over x minus 2 and y equal x plus 2, those are not the same thing. One's simplified to be the other, but these are actually different because they have different domains. You see, 2 was a problem for f of x, we said, but 2 is not a problem here. I can let x be 2 and get 4. So 2 is actually the one number that makes these two expressions different from each other. Okay, so as long as we're not using 2, it's going to be like we're drawing a line. Since we're drawing a line, there's not going to be any asymptotes at all. And I can skip step 4 because I didn't have any asymptotes here. Step 5 is getting the intercepts. When you set the function equal to 0 and solve, you get x equal 2 or x equal negative 2. We've already said that x can't be 2, though, so I'm throwing away that number. Of course, an easier way to do the x-intercepts could be to just set the simplified form equal to 0 and solve. That eliminates the 2 that would come up in the calculation. And to get the y-intercepts, if you plug 0 into the function, you could plug it in the simplified form here. You get 2 in return. And so these 2 points would be my 2 intercepts that I've got. Now, if x is 2 and I plug that into the simplified form, I get 4. Okay? The point 2, 4, I want that not to be on the graph. I've got that indicated with an open circle. And I mentioned that 2 is the one number that makes these two expressions different. Okay? As long as you're not using 2, it's going to be like you're drawing a line. So we've taken care of the one number that makes these different from each other. Of course, the rest of the graph would be just a solid line then. So what we end up getting is a line with a hole in it. In general, anytime you have a function that simplifies and you have expressions canceling like what we see here, the corresponding zeros are going to create holes in the graph. Okay? So at 2, 2 is the 0 of these two factors here. I get a hole in the graph. In general, that's going to happen. Okay. Problem 8 is the last one. We want to find a rational function that might have the graph given below. The idea here is to use the information that I've gone over previously on this worksheet here. So of course I need to set up a fractional form here since this is a rational function. Also, I see that I've got 2 vertical asymptotes at x equal 2 and x equal negative 2. Now how did that happen? Well, it's because 2 and negative 2 were a problem in the denominator. So I want to make sure that those numbers are thrown away. X squared minus 4 therefore would go in the denominator since 2 and negative 2 would be a problem in the denominator. Also, whenever the degree of the top is the same as the degree of the bottom, you're going to have a horizontal asymptote, but it's not going to be at y equals 0. It's going to be at y equals some other number. And the the shortcut to that is just to compare the leading coefficients in front of the terms. If you have a 1 in front of x squared up top and a 1 in front of x squared down under, y equal 1 would be the equation of the horizontal asymptote. Okay? So I'm going to want an x squared in the numerator, since I see I've got a horizontal asymptote right here at y equal 1. I wouldn't want x because that would mean that y equals 0 is a horizontal asymptote, and I don't see that. Okay, and so that'd be the answer for problem 8 here that we're getting. The homework problems that I've got listed in the book are on page 336, so you'll want to be sure to look at those when you can. And at this point, we're now done with section 4.6.